All right. So the last section in chapter 2, we're going to look a little closer at the, we've been talking about linear equations throughout the entirety of chapter 1 and linear modeling in chapter 2. So what we're going to do in this chapter is we're going to look a little bit more closely at the slope. We're going to look at some different interpretations of the slope. We're just looking at the slope in a little bit more detail in this section, and ways we could tell things are linearly related and stuff like that. And but before we actually get into that, let's look at this concept called rate of change between two quantities. So, something you're probably familiar with in like a basic math class, or you've seen already, is a ratio. And all a ratio is a fraction. But this fraction really is a comparison of a to b, and we just write it as a fraction a over b. A unit ratio is where the b value is 1. So, there are literally hundreds and, if not, infinite types of examples of ratios and unit ratios. We work with them all the time in the real world, whether you realize it or not. One such example is right here. So, suppose the ocean's tide increases steadily by 12 inches in the past 4 hours. Write its ratio. Well, this is a comparison of 12 inches to 4 hours. So writing this as a ratio is just 12 inches over 4 hours. All we're saying here is we're comparing 12 inches to 4 hours. This is a ratio of one unit to another unit, or one quantity compared to another quantity. Now, let me ask you this. Can this be written as a unit ratio? So remember, a unit ratio is where the denominator value is 1. Well, actually it can. Why can it be written as a unit ratio? Because 12 over 4 reduces to what? 3 over 1. That reduces, right? 12 over 4, that reduces to 3 inches per 1 hour, because 12 divided by 4 is 3 over 1, which is 3. So this ratio could be written as a unit ratio by just reducing the fraction. That's it. So in other words, 4 hours, the ocean's tide increases 12 inches for every 4 hours, or I could say it increases 3 inches for every 1 hour. I know I wrote plural, but you get the idea. There are many examples of unit ratios. This is just one of them. Unit ratios could be dollars per hour, right? Or miles per hour. These are things we work with all the time. If you have a job and you're paid per hour, then that's a unit ratio. $10 per hour, $15 per hour. If you drive, you go 60 miles per hour. This is just common sense. These are unit ratios. We work with these things every day. Now, there is a formula for calculating the rate of change between two quantities, and we call it the average rate of change, or just the rate of change formula. And guess what? Here's the big surprise. It's the exact same formula as the slope, except we're just illustrating it differently. This right here means the change in y over the change in x. And that's what that triangle symbol means. It means change in. And the average rate of change, or the rate of change, is the same thing as the slope formula, except we could just, it has another interpretation. We could just call it the rate of change between two quantities. The rate of change is an average change if the change is steady. So, like the example we just did, it was the ocean's tide increased steadily, so that was an average rate of change. So, if I look at this example here, the number of Americans who fly to Europe has decreased approximately, steadily, there's that word steadily again, from 13.3 million flyers in 2007 to 10.8 million flyers in 2011. Find the average rate of change of Americans who flew to Europe. So, okay. So let's let's find the average rate of change. So 13.3 million in 2007 to 10.8 million in 2011. So since we're starting here and we're going to here, this is the first point and this is the second point. All right, so when I find the rate of change, or the average rate of change, that's going to be y2 minus y1 over x2 minus x1. Now, the y value is the millions of flyers, okay? Because that's the dependent variable. The number of flyers to Europe depends on the year. So the dependent variable is y. And since this is the second pair, or since this is the second point, y2 is going to be 10.8 million flyers. So 10.8 minus the first one, which is 13.3. Now what I'm going to do here that I haven't been doing with the slope formula is I'm going to include the units here because that's important when we're looking at rate of change. Dollars per hour, miles per hour, the units are important. So these values represent million flyers. All over x2, which will be the second independent value, which is the year, so it's 2011. Notice how I'm using the year here and not the number of years because there's no variable description here, so I could use either one, that's fine. Or, well, I could use the year itself, that's fine, I should say. So that's 2011 minus the first one, which is 2007 years. So now when I do that computation, whip out your calculator. So 10.8 minus 13.3 is negative 2.5 million flyers. All over 2011 minus 2007, 4 years. So now this is a ratio. So that means for every 4 years there are 2.5 less, because it's negative, million flyers from America to Europe. But if I want to reduce this, I can. So negative 2.5 divided by 4 gives me negative 0.625. There it is in my calculator. Negative 0.625. So that's negative 0.625 million flyers per, now since this is the value, that's going to be over 1 per 1 year. Because that's what this reduces to. I just did that division in the calculator and got that. And this is the unit ratio. So this right here is the unit ratio, where the denominator is 1. So find the average rate of change of number of Americans who flew to Europe. So what this really means is, and I'm going to make this interpretation right here, So 0.625 million is actually 625,000, right? If I did that, if I multiplied that by 1 million, that's negative, so it's 625,000. But the negative sign means that there's less, not more. It means it's decreasing. So that means there are 625,000 fewer Americans who fly to Europe every year. And that's how you would interpret that. This right here is the average rate of change, and that's how you interpret that. Okay, so because this was negative, you know, if the average rate of change is positive or negative, that means as one is increasing, the other one's decreasing. Or as one is decreasing and the one's increasing, vice versa. So remember how I just said not too long ago that this formula, the average rate of change, is identical to the slope formula? Well, that's not a coincidence. Right here. Slope is a measure of rate of change. And that's what it is. The slope is actually a measure of the rate of change. That's why their formulas are identical to each other. And you know what's funny is that this concept right here, slope, rate of change measure, that right there is the study of calculus, which, you know, scares a lot of intro to algebra students, but that's what calculus is. It's the study of rate of change, among other things. But that's what, you know, calculus actually, its word is derived from the word calculation or calculi, which is change. So, yeah, it's interesting. Slope is the rate of change of two quantities. All right, so since we can make that, you know, since we can make that assumption that the slope is a rate of change, we can, you know, say the following two things are true. Now, this is just the opposite of this statement, like in reverse order. So if there's a linear relationship between two variables, then the rate of change is constant. Or I could say the opposite. If the rate of change is constant, then there's a linear relationship between x and y. So all this is saying is constant rate of change implies linear. And I could say the opposite. Linear implies constant rate of change. You could say one or the other. That's all that's saying. In order for something to be linear, it implies that it's a constant rate of change. If it has a constant rate of change, then it's linear. I could go left to right or right to left with this statement. All right, let's look at this problem. So this concept is very useful for finding a linear model. So in this example, a company's profit was $10 million in 2005 and has increased by $3 million per year. Let P be the annual profit in millions of dollars at T years since 2005. So the independent variable is T and the dependent variable is P. Okay. Question 1. Is there a linear relationship between T and P? Explain why or why not. There is. Why? Why is it linear? Well, the problem gives it away. What did we just get done saying? That if you have a constant rate of change, that means it's linear. So do we have a constant rate of change here between time and profit? We do. We do. It says right here. I'll use a different color. the profit increases by $3 million per year. See how the units are dollars per year? That right there is a rate of change, which is dollars per year. So this rate of change of dollars per year, that's a constant. That's telling you per year it changes by 3 million, 3 million, 3 million, and it's increasing, by the way. So that right there is a constant rate of change, which means it's linear. So yes, this is a linear relationship because the change between T and P is constant. All right, find the p-intercept of this model. So, all right, the p-intercept is the value of p when the other variable, t, equals 0. Alright, so the p-intercept is the value of p when t equals 0. Alright, well, when t equals 0, what does that mean? Let's go to here. T years since 2005. Alright, so when t equals 0, what year is that? That's going to be the year 2005, right? 0 years since 2005 is 2005. So what we're saying here is, what is the value of this company in 2005? That's what the p-intercept is. I should say, what is the value of the company's profit? Because that's what it is specifically. It's a company's profit. So what is the value of the company's profit in 2005? That's what this is saying. Because 0 years since 2005 is the year 2005. Well, the problem tells you that right here. A company's profit was 10 million in 2005. There it is right there. So the p-intercept is 10. All right, so that's right there in 2005. So that's the p-intercept. So it's 10 million in 2005. Which means the p-intercept is 10. Now if I want to write this as a ordered pair, right? T is 0, comma, 10. That's the p-intercept right there. All right. Find the slope of the linear model. Again, slope is a rate of change, isn't it? So it's going to be a comparison of the two values. It's the rate of change between dollars and years. I already identified it. Where is it? It's right here. $3 million per year. So the slope, which is the rate of change, is $3 million per year. Or I could just say slope is 3. Alright, I have my slope, I have my p-intercept, which in this case is my y-intercept, so I could find my equation of the linear model. So that means p equals, alright, if I use this, y equals mx plus b for a reference. P is my dependent variable here, right? So my slope was what? 3. X plus, and my y-intercept, which is this, my y is p, so that's my p-intercept. We just did it here. It's 10. Boom. So my equation of the linear model, p equals 3 x plus 10, you know what? I'm not going to use, I should be using T, not X, my bad. It should be 3T. So that's it. That right there is the linear model, or the linear equation for the company's profit since 2005. So, you know, that makes sense, right? Because if I plug T equals 0 in here, that goes away and I get 10, which is exactly what it was. It's 10 million in 2005. So if I want to find out the profit in 2010, well, that's 5 years since 2005. So I plug in T equals 5 here. 5 times 3 is 15, plus 20, or plus 10 is $25. That's $25 million. So in the year 2010, the company's profit would be $25 million. And you could keep going on. If I want to do the year 2020, that would be 15 years. So plug in 15 here. 15 times 3 is 45, plus 10 is 55 million in 2020. And you get the idea. All right, so, you know, when it comes to setting up a linear model, that's, you know, we just did it piece by piece here. But so how do I know this is right? I mean, I know it's right, but how do you know it's set up correctly? How do you know that? Well, we do this by using unit analysis. And, you know, you may have seen this before if you've taken like a chemistry or physics course in high school, or, you know, physical science or whatever. So, unit analysis of a linear model, all we're really doing here is we're looking at the units of the expressions on both sides of the equation. If the units on both sides match, so if the units on both sides of the equal sign match, then the equation of the model is considered correct. Alright, so using the previous examples model, let's perform a unit analysis below. Okay, so let me go back and rewrite this for reference. So P equals 3T plus 10. Now I'm writing it big like this deliberately because I want you to, because we're going to be writing some stuff underneath it. So P equals 3T plus 10. I wrote 3 times T. I emphasize that because I just want you to see the unit analysis here. So all we're really doing is we're looking at the units of each quantity in this linear model. And if they equal both sides, then it's correct. Alright, so what did P represent? P represented the profit of the company. What are the units of profit? Dollars. So the units of P are going to be dollars, equal sign. So ideally, I want the units on the right side to be what as well? Dollars. Then the unit analysis will match and the equation I know will be set up correctly. Alright, what are the units of 3? Well, 3 was the rate of change, right? Was dollars per year. Okay. Variables and numbers. We're looking at the units of everything in this equation on both sides. So the units of 3 was dollars per year. And that's being multiplied by T. What are the units of T? That's time. That's the year. So that's being multiplied by years. Plus, what are the units of 10? What does 10 represent? 10 was a unit of money, right? It was the company's profit in 2005. So the units of 10 was in dollars. Okay, so now that we know the units of each quantity, let's see if the units match. So I still have dollars on the left. That equals, so when I multiply dollars per year times years, what happens? The years cancel. Right? Because the years down here because the years in this quantity is in the denominator. The years here is over 1, which is in the numerator. They cancel. So I'm left with dollars here, plus dollars. Stuff with dollars plus stuff with dollars is stuff with dollars, and that equals the stuff with dollars. The units on the both sides match, so that's correct. So I performed a unit analysis, so the equation is correct. I know it's set up correctly because the units balance out. All right, let's look at this example. So a driver fills her car's 12-gallon gas tank and drives at a constant speed. Oh, there's that word again, constant. I'm going to underline it because it's important. The car consumes 0.04 gallons per mile. We're going to let G be the number of gallons of gas remaining in the tank after she has driven D miles since filling up at the gas station. Find the equation of this model and perform a unit analysis on it to verify it's correct. Okay. And before we do that, we've got to know what the independent and dependent are. So what's the independent variable? What's the dependent variable? Well, G is the number of gallons of gas remaining in the tank of your car after she has driven D miles since filling up at the gas station. So let's think about that. Which one's dependent, G or D? So, well, it should be pretty obvious that G is the dependent variable, right? Because the number of gallons of gas in your tank depends on how many miles you've driven, right? The more you drive, the fewer gallons are going to be in your gas tank. So the independent variable here is how many miles you drive. And the dependent variable is how many gallons of gas are in the tank, right? Number of gallons in your car depends on how far you've driven. As you drive, your car uses gas. It's pretty common sense there. So, all right, now that we know that, we want to set up a linear equation. So we want to find an equation of this model. So that means we want to find something that takes the form y equals mx plus b. But if I use the variables in the problem, independent, right, that's x, right? So I'm going to replace x with d, and I'm going to replace y with g. So if I use the variables that I have, this is going to be G equals M times D plus B. So once I find the slope and the G-intercept, I have my model. Okay. And then once I have my model, I want to check it using a unit analysis. So is there any quantity in here that implies is the value of the slope or y-intercept? Well, it better be in there somewhere, or else we can't do the problem. Duh. So let's look at this. 0.04 gallons per mile. Oh, there's that thing again. See how it has units per unit? What is this? This is a rate of change. The rate of change is a slope. Ha. So the slope is 0.04 gallons per 1 mile. So we know what the slope is. Alright, so now this thing right here, that's the G-intercept. Right? Because it's G, not Y. Ordinarily it'd be the Y-intercept, but the variable here is G. So the G-intercept is G when D equals 0. Right? What is G when D equals 0? So if we interpret this, this means what is the number of gallons in the gas tank when we didn't leave the gas station. So since filling up the gas station, this is D miles since we filled at the gas station. Well, if D equals 0, that means we haven't driven since we filled up at the gas station. So what does that mean? That means G is going to be the number of gallons in the gas tank when the gas tank is full. How big is the gas tank? 12 gallons. So this means, I'll just write that out, number of gallons when we have a full tank of gas, because we haven't driven since we filled up. So what is that? 12-gallon gas tank. So that means G equals 12. So the G-intercept is 12, which is this value. So that's the G-intercept. Alright, so if I bring this all together, so now I know this. So my equation is G equals my slope. Now, is my slope positive or negative? So that's the last thing we have to do here. Is my slope positive or negative? How do we know? Well, look at this value, look at this word right here, consumes. How, the level in the gas tank is going to do what as you drive? It's going to go down. That's what this word consume means. So the value of the slope here is going to be negative. So my slope is negative 0.04. I know I kind of omitted that when I did it here, but I want you to be able to see that. This means it's consuming, which means it's negative. So, in the previous problem, the company's profit was increasing, that's why the slope was positive. Here, the car is using gas, which means it's negative. So my equation is negative 0.04 D plus 12. That's my model. And this model measures the number of gallons in your gas tank since filling up at the gas station. So if I drove 10 miles since filling up at the gas station, then just plug in 10 here for D and then see what G is. So if I did that, if I did that just for, for giggles, negative 0.04 times 10 plus 12, 11.6. So if you've driven 10 miles, you have 11.6 gallons in your car. If you've driven 50 miles, now you have 10 gallons in your car, and so on. Okay, so why don't we do a unit analysis here? So a unit analysis will be pretty sweet. So what are the units of G? G is the number of gallons in the gas tank. So G, the left-hand side of my equation, is going to be gallons. What are the units of negative 0.04? Well, we have it right here, gallons per mile. That's being multiplied by D. What are the units of D? Miles. Plus, what are units of 12? Well, 12 is a gallon gas tank. The units of that are gallons. So let's see if the units match on both sides. So what happens here? Gallons per mile times miles. What happens to the miles? They cancel. So I'm left with gallons on the left equals, this reduces to gallons, plus that's already gallons, and something in gallons plus something in gallons is also in gallons, and that equals gallons, which means it's correct. So that's my model, and that's how I know it's set up correctly. That's it. Okay. So again, just to finish this section off, interpret the slope of this model, which is right here. So how do we interpret that? Well, since this is negative, this means the car consumes 0.04, and it consumes 0.04 gallons, right, for every mile driven after filling up at the gas station. So that's how you interpret the slope when we have a comparison of two different variables. You know, you could also say for every mile the car drives after filling up at the gas station, the car consumes 0.04 gallons. You could say that as well, or you could say it the way I wrote it. There are multiple ways to interpret things, but yeah. So that's it for this section, and that's it for the chapter. So, you know, Chapter 2 was more about linear modeling than anything, and like, you know, just using linear models to describe data. Now, we only do linear modeling in this course, but if you do take college algebra, you'll see other kinds of modeling. And, you know, when it comes to linear modeling, just to refer, you know, refresh. Linear modeling is when you have a constant rate of change. And, you know, you'll see with other kinds of modeling, like quadratic modeling or exponential modeling, that is not the case. All right, so, you know, that's the end of this chapter, 2.4, and that's, well, this section, and that's the end of chapter 2. So, yeah, so in the next chapter, we're going to start looking at systems of equations and stuff like that. So, yeah, so that's the end of this video.